This is question 2 from revision quiz 2, and I think it's a good one to do because it's a kind of confusing one. So it says a simple random sample of size n equals 300. So we might as well write down our parameters as we go. N equals 300 is taken from a not normal distribution, not normally a normal population, or it might be, we don't know. And the sample mean and standard deviation are x bar is equal to 24.7, and this is the sample standard deviation, 7.4. So we don't know the population standard deviation, and we don't know what the distribution is of the underlying population. And it says give to two decimal places the limits. So we want a 95% confidence interval again. So alpha is going to be 0.05. So what makes this tricky is you're given here that n is equal to 200. So the question is, am I going to use a t-test? Am I going to use a z-test? What exactly is going on? So when you look through the book, basically what it tells us is that for an underlying normal population, we use the z-test, and the z statistic actually gives an exact sample distribution regardless of the sample size, and all we have to do is adjust our variation depending on the size of the sample, or adjust our standard deviation based on the size of the sample. But for a non-normal population, what it says is that same thing, that same z-score gives a good approximation when n is greater than 30. So if we know the standard deviation, but in this case we don't, and n is greater than 300, is greater than 30, 300 is obviously 10 times 30. If n is bigger than 30 and we knew the population standard deviation or variance, then the z statistic would be a reasonably good approximation, even though it wouldn't be exact. And the book gives some examples of, as the sample size go up, you can see that the distribution looks more and more like a normal distribution. In this case we don't, we've just been given the sample standard deviation, and so we know we're going to have to use probably a t-score. Now the t-score, you'll recall, gets closer and closer again to the z-score as the population size goes up and up. So we say, oh, okay, n equals 300, I can just use z. Well, actually the z is going to be a reasonable approximation again, but the t-score is still going to be the exact value. So for these ones, what you'll find is that the result given for a non-normal population is always given as using the t-value, the t-score, using degrees of freedom n-1. So in this case, 299. So if you tried to look that up in your tables, that's obviously not going to be there. But if you went and used the biggest t-score, then that would probably be okay. And you'll see that the variation from the z-score can be around 5%. It's not going to be too enormous. So that's really the tricky bit of getting your head around these ones, is some of them are exact, some of them are approximate. When is it okay to use an approximate? Well, if it's greater than 30, if sample size is greater than 30, then that approximation is usually okay, but why use the approximation when you can get the exact? So we've got access to Microsoft Excel, so we just use that to find the exact value in these ones. So I hope that didn't confuse you too much, but basically in this one we know it's a we don't know it's a normal population, so we're going to use the t-score even though we've got a big sample size, because the t-score is going to give us our exact value. So what we do is we say that the lower limit, well, the mu is going to be equal to, again, x bar plus or minus, and it's going to be our t-score with alpha on 2 and n-1 degrees of freedom multiplied by s over root n, and that's going to be our error. So in this case we've got x bar is 24.7 minus, well, plus or minus, and then we've got, let's see, so t of alpha over 2, so point in case in this one our t table goes up to 90, so if we put in an alpha on 2, so it's 0.05, we get 1.987, which probably wouldn't be too far wrong. You can see that the alpha over 2 is 1.96 for a z-score or a z-score, so there's a little bit of difference between them. And if you actually went up to n equals 300, or degrees of freedom equals 299, you'll see that the difference is a little bit more again. In fact, I'll just use Excel and find out what that is right now. So for via Excel, if we do a t inverse two-tailed with an alpha of 0.05 and degrees of freedom 299, it actually gives us the t-score of 1.96793, or we'll just round it to 1.97. So you can see even at the end of our table with t equals 90, we get 1.987, so it comes down a bit further. So it's getting closer and closer to representing the z-score. So 1.97 versus 1.96, not too big a difference, but still gives you a slightly different answer. The other thing to notice is that the t solution, the t distribution here, so this is part of our error. So the t-score we've got is 1.97, which is slightly larger than if you use the z value. In other words, our t distribution gives us a slightly more conservative result, which is why it's recommended to use this one if you don't know which one to use. So let's keep on going. 1.97 multiplied by 7.4 divided by root 300. And that's going to be equal to 24.7 plus or minus 1.97 times 7.4 divided by root 300. That's 0.842. So this is going to be equal to 24.7 minus 0.842. So 23.86. It's less than or equal to mu. Less than or equal to 24.7 plus 0.842, that gives us 25.54, and so our lower limit's going to be 23.86, our upper limit's going to be 25.54, and we're done.